Hi, everybody. Thank you for listening today. I'm going to give I'm going to emulate the talk I gave earlier in my PhD defense. The title of my thesis is Learning Patterns with Kernels and Learning Kernels from Patterns. In this talk, we examine applications of Gaussian process regression, also commonly known as kriging or kernel interpolation, to problems with the aim of learning patterns. The application of kernel interpolation requires the specification of a kernel, best modeling the patterns, the structure, the regularities in a particular data set. This interpolation is then used so this interpolation with this model kernel is then used to make predictions and learn patterns on the data. This talk will be split into two parts. The first, where the model kernel is derived is derived from the context, the assumptions, the setting of a particular problem. And the second part will be where we learn the kernel directly from patterns within the data. We look at the image classification problem in the second half of this talk. Images are extremely high dimensional, and it's unclear exactly how to specify a kernel which best models the covariances of an image, which makes it necessary, or which makes it desirable to learn a kernel directly from the data. It's desirable to learn a kernel directly from an image data set. First we'll briefly introduce Gaussian process regression. Here we have the prototypical supervised learning problem, where U is some unknown relationship between two quantities, X and Y. Based on a finite number of measurements, the question is, how can we approximate this relationship U? Here we have the definition of a Gaussian process. It's just a generalization of a Gaussian random vector to a domain omega. It's specified by a mean function and a covariance function, or covariance kernel. In order to apply Gaussian processes to this learning problem, we model our data with some model kernel. Here we take it to be centered, and we condition it upon our observation points Ti, Yi, and we interpolate the data with, or in other words, we estimate the relationship between T and Y with this conditional expectation of the model kernel on our of our model kernel conditioned upon the measurements, or the observations, or the training set. And this interpolation is dependent on the model Gaussian process, since in this case we assume X to be centered. This boils down to a selection of model kernel K. This is the main challenge typically in using Gaussian process regression in applications. It can potentially be unclear which model kernel best describes the correlations within any particular data set. But in the first couple of problems, we will look at, we will be able to design a kernel based on the context and assumptions of the particular problem. We can use GPR with this model kernel to learn patterns and make predictions on future data. We also note that this method is very versatile, in that we apply Gaussian process regression to problems where one might not think of Gaussian process regression as a viable approach to the method, or as a and we show how GPR can be used side by side with existing techniques within the settings of each of the problems that we present. So the first problem that we look at is a variant of Donahoe's denoising problem. He assumes that F is in some smoothness class based on a finite number of measurements that are corrupted by noise. The question is, how can we accurately recover F in L2 norm? And Donahoe's answer is to soft threshold a certain class of wavelet coefficients. And he shows that this is indeed a near minimax denoising with in L2 norm, meaning that this recovery is within a constant, is within a fixed constant of a near minimax, of a minimax denoising. It's within a constant of a minimax denoising. The setting of the problem that we'll address in this work, we take omega to be some bounded domain. We take L to be a linear operator from a Sobolev space to its dual, and we take F to, and we take its associated energy norm, and we again ask if we have some noisy observation, where in this case U isn't assumed to be in a smoothness class. Our prior assumption in this problem is that LU has a bounded L2 norm. The question is, how can we accurately recover U in this energy norm? Note that M and sigma are both known in this problem, meaning that they aren't just arbitrary, or they are so M and sigma are set in the are assumed to be known in this problem. M governs the strength of the signal, and sigma governs the strength of the noise. So knowing both M and sigma essentially tells you the signal to noise ratio in eta. All right, so to see this in action, we look at a case where omega is a unit interval. L is a second order elliptic partial differential operator. Here we take A to have, or we take the coefficient A to be rough. And here we have 5 examples of LU being in L2. Now, these all have characteristic patterns visually. This can be explained due to the fact that LU is in fact an L2 function. The placement or the inflection points in each of these U's can be observed to occur at consistent points in time. Note, however, that when we add noise to the signal, these nice patterns are lost in eta due to the noise. The main result of this work is that there exists an efficiently computable recovery such that there exists an efficiently computable recovery that is near minimax. And with high probability, and as a bonus result, we have that this recovery with high probability is smooth relative to signal U, to original signal U. And this near minimax denoising we prove results for turns out to be it turns out to be a Gaussian conditioning. This result was proved and inspired from my advisor Houman Owadi's operator adapted wavelet framework. They are exactly what they sound like. They're wavelets adapted to a particular operator. In the context of this problem, we just take that operator to be the partial differential operator L. And these wavelets are hierarchical. They can be defined, or they are defined with a hierarchical set of measurement functions. here we take pre-Haar wavelets, which are simply indicator functions on subdomains of omega. These subdomains are hierarchical. And these measurement functions can then be used to define operator-adapted pre-wavelets. These pre-wavelets turn out to be precisely Gaussian conditionings based on outputs, or based on measurements using the pre-Haar wavelets or the measurement functions. These operator-adapted pre-wavelets can be shown to be optimal recovery splines, in that this is the optimal recovery of U in energy norm in energy norm associated with L, based on the measurements on the kth level measurement functions. So this is our kth level optimal recovery, and it turns out that it is also exactly a Gaussian conditioning based on the measurements on the kth level. We can extend operator-adapted pre-wavelets to operator-adapted wavelets, and we can decompose a signal U into operator-adapted wavelets, and we call this the operator-adapted wavelet, or gamblet, also known as gamblet transform. The near minimax denoising itself is actually just a kth level optimal recovery. K is selected depending on, or the level itself is selected depending on the signal to noise ratio assumed in the problem. Note that if we take a level too low, the signal is overly smoothed, while if we take a level too high, the signal isn't sufficiently denoised. In this example, the near minimax denoising is the fourth level optimal recovery. This is nice because it removes almost all the noise, but also it recovers some of the nice characteristics in the signal U. It recovers some of the patterns in signal U lost in the noise. This near minimax recovery is compared to three other recoveries. First two are inspired by Donahoe's thresholding approach. We threshold the coefficients of the gamblet transform. And again, note that these operator-adapted wavelets are Gaussian conditionings based on these measurements. So in fact, we are thresholding this transform with GPR with wavelets that are Gaussian conditionings. And the final one we compare it to is called a regularization recovery, where we optimize V in this norm, and in all measures of error in energy norm and in L2 norm, we find that our near minimax recovery is numerically better than the other three. So we can look at this problem in 2D, and in the example where the operator L is a graph Laplacian. However, in this example, the nice minimax results that we proved in the Sobolev domain don't apply in this graph domain. So to summarize the operator-adapted wavelet approach to denoising, it boils down to selecting a model Gaussian and conditioning our noisy observation using a particular level of hierarchical measurement functions. This then turns out to be it turns out to be a near minimax denoising. And as a bonus, we can incorporate Donahoe's hard and soft thresholding approach into the operator-adapted wavelet approach, showing GPR and a traditional method of denoising working hand in hand with each other. Okay, so moving on, we're going to discuss the mode decomposition problem, the signal mode decomposition problem. Each mode is defined as a nearly periodic trigonometric signal, the amplitudes of which, the instantaneous amplitudes of which are smooth. The instantaneous phase is smooth, as well as its derivative, which is called the instantaneous frequency. And the problem and the question we ask is, if we observe a composite, or if we observe a sum of these modes, how can we individually estimate each one of the modes? The direction we're going in the work, in this work, is asking ourselves if we can generalize this problem to non-trigonometric based waveforms, meaning we replace this cosine with some arbitrary periodic function. But also, what if we don't even know what this unknown base waveform is? So to illustrate, we have mode 1, mode 2, mode 3. They all have nice, nearly periodic patterns within each of the signals. However, when we combine them, the pattern is lost. One of the main, or one of the most popular approaches to mode decomposition is something called empirical mode decomposition, invented by Norbert Wang. The main the approach to this is to compute a lower envelope and an upper envelope for the signal. In the traditional implementation of empirical mode decomposition, the local minima and local maxima are found and are connected with cubic splines. The mean of these two envelopes is calculated. Then we subtract off this mean signal from the original signal, and we iterate this until the mean goes to 0. We take the resulting signal and denote that as the first mode. We subtract that off, or peel it off, if you will, from the original signal, and we repeat this process until all the modes have been estimated. So this is, again, very popular in applications, but it's hard to obtain theoretical guarantees on accuracy and convergence. A second very popular approach is called Synchrosqueezing. What this involves is computing the continuous wavelet transform. Here, A refers to a frequency scale, B refers to a time scale, V is the signal, and psi is some wavelet, some mother wavelet. So if we take the continuous wavelet transform of an example with 3 modes, this is what we see. We have mode 1, mode 2, mode 3. However, note that in this transform, the estimates of frequency aren't very sharp. So to address this, what synchrosqueezing does is it estimates an instantaneous frequency at each time frequency point. It reallocates the energy in the continuous wavelet transform in the synchrosqueezing transform. So here we have sharp estimates of the frequencies of mode 1 at each time, frequencies of mode 2 at each time, and frequencies of mode 3 at each time, or instantaneous frequencies. My apologies. So now, if you want to make an estimate of each mode, what you do is you draw bands or sausages around each one of the modes in time frequency space, and you just integrate the synchrosqueezing transform, and that'll give you an estimate of each one of the modes. Some shortcomings of SST is that it's unclear how to address non-trigonometric based waveform signals. Also, what do you do when you don't even know the waveform, and also when frequencies cross? So that just means So hypothetically, if you had another if you had another mode with frequency going along here and it intersects with you have two modes with intersecting frequencies, that's what we mean. So synchrosqueezing is unable to is unable to accurately separate those two modes. So to illustrate so to introduce the non-trigonometric variant of this problem, all we do is we replace the cosine with some known arbitrary periodic function. In this case, we take that to be a synthetic EKG wave. Here we have mode 1, mode 2, mode 3. And the question is, from the composite signal V, how can we recover mode 1, mode 2, mode 3? Yeah, so we can also do this for any arbitrary waveform. So here we have this plotted out for a triangle wave. To illustrate our approach, we look at the synchrosqueeze transform of an example or of a mode decomposition example with three modes and a non-trigonometric base waveform. So in this case, we see base frequencies here, here, and here. However, we're going to have overtone frequencies. So if this is omega 1, then this is going to be 2 omega 1, 3 omega 1, 4 omega 1. And this just comes from the fact that it just comes from the Fourier expansion of the base waveform. So note that the lowest frequency mode has no interference from overtones, unlike the second and third lowest base frequency mode. So the strategy becomes to estimate this lowest frequency mode. Now, the main component of our algorithm to approach this problem is to use GPR to refine the lowest frequency mode phase and frequency estimates. So using SST, we can estimate the phase and frequency of the lowest instantaneous frequency mode. And then we can use GPR to obtain refined estimates of the phase and frequency as well as an estimated amplitude of the mode. The approach that we take to do this is we take a windowed signal of a windowed version of V. So in this case, tau is the center of the Gaussian window. The width of the window depends on the instantaneous frequency as well as hyperparameter alpha. Right, and this is just a windowed version of V. The model Gaussian that we select looks like this. It boils down to having this Gaussian window, and it has a cosine component and a sine component. And now with GPR, the point is we want to estimate the coefficient, the correct coefficient in the cosine component and the correct coefficient in the sine component. So what this looks like is we're estimating the true signal with cosine with cosine of our SST phase estimate plus some coefficient times the sine of our SST phase estimate. So in doing so, we can obtain an amplitude. We can obtain an estimate of the amplitude as well as an estimation of the error in our phase phase estimation from SST. And we can iterate this process until it converges, and then we here have an estimation of the lowest frequency mode. We peel this from our signal. So once it's peeled, we look at the SST transform, or sorry, the SST of the peeled signal. Now the second to lowest base frequency is mostly or has minimal interference. We can estimate it, we can peel it. Now our third to lowest frequency has minimal interference. We estimate it, peel it. Now we have nothing left, and so we terminate our algorithm with estimations of our first, second, and third modes. So here we have some numerical results for this EKG base waveform example. We have error rates in the 10 to the -3 to -4 range. In the slightly easier triangle wave example, we have error rates closer to the 10 to the -6 to 8 range. So moving on to the unknown waveform variant of mode decomposition, we assume that that the waveform is now unknown. And now when we ask to individually estimate each mode, not only do we have to estimate the amplitude and the phase, but we also have to estimate the waveform. Now in the defense, I was asked about the well-definedness of this construction. One way to ease concerns is to say that yi is scaled and dilated such that it has a such that it has a unit Fourier coefficient, or it has a unit base Fourier coefficient. So to see this in action, we look at mode 1, mode 2, mode 3 with their corresponding waveforms. Now, again, when we combine the three signals, or the three modes into V, the patterns from each of the waveforms are lost when we do this composition of modes. Now we ask how might we learn these waveforms, and now of course the answer is with GPR. We use the previous method to estimate the instantaneous phase of our lowest frequency mode. Then we can leverage that with GPR to estimate the base waveform. The way this works is we again take our Gaussian window, and here we model the Fourier coefficients of the base waveform. We use GPR to estimate the coefficients of the Fourier transfer, or the Fourier series of the base waveform. And how this looks in, I should also mention that the CKC. So this is an estimate of the kth overtone cosine component of the base waveform at time tau, with estimated phase theta and signal v. So to see this in action, here we estimate the third cosine component in the Fourier series. We look at triangle waves, so the true coefficient should be 1/9. In this range, the estimation is pretty good. However, near the borders of the interval, we have interference, and that just comes from the fact that 3ω1 and ω2 are similar around the borders of the interval. To get around this issue, we can just take a histogram of all the estimated values of tau, and we find that the most common value is indeed approximately 1/9, and we take the most common value to be an estimate of the third cosine Fourier coefficient in the Fourier series of the base waveform. Okay, so here we have an example with unknown waveform mode decomposition. Amplitude and phase estimations in these examples turns out to be on the order of 10 to the -4 to 10 to the -5, where and further, the estimation of each waveform is on the order of 10 to the -4 to 10 to the -3. We can also extend this to a case where the waveforms, where the instantaneous frequencies intersect, to where an amplitude vanishes, and also when we add noise to signal V. Error rates in this case are in the 10 to the -2 range. Okay, so to summarize our approach for mode decomposition, we borrow ideas from synchrosqueezing and empirical mode decomposition. We use synchrosqueezing to identify and estimate the lowest frequency mode. Then we can use GPR to refine this estimate to the point where where we can refine this estimate to the point where we can eliminate almost all of the contributions from the lowest frequency mode. Then further, if the waveform is unknown, we can use GPR to estimate it as well. And finally, we borrow the peeling idea from empirical mode decomposition, and we iterate this process until all the modes have been identified. Possible future work include obtaining convergence guarantees and accuracy guarantees on this refinement process. Also, we can ask if this process can be made more efficient with an analytical computation of the convergence. So instead of doing an iteration, we can ask if we can just analytically compute it, analytically compute the convergence. Unfortunately, in this project, we didn't have sufficient, or we didn't have the time to apply kernel mode decomposition to applications. One application one possible application includes comparing KMD to a proprietary sound wave algorithm, which is also able to separate vocal. It's able to separate vocal waves which might have crossing frequencies into two different vocal waves. This algorithm costs something like $499, and it would be interesting to compare the performance of our mode separation with crossing frequencies with theirs. Okay, so in the second part of our talk, we're going to look at learning kernels directly from the data. So to motivate the need for this, again, here we have the prototypical supervised learning problem in a low number of dimensions. It's not very difficult. However, when we move to contexts where the data has thousands of dimensions, such as an MNIST or a CFAR, these are the canonical image databases in machine or in image classification in machine learning. How do you construct a kernel that has a high covariance between this frog and this truck versus and has a low covariance? I'm sorry. How do you construct a kernel that has a low covariance between this frog and this truck, and a high covariance between this truck and a slightly different looking truck? That is a very difficult problem, especially considering there's something like 3,000 dimensions in CFAR. So right, the main challenge is what kernel should be selected, especially in these high dimensional settings. Our approach is to use kernel flows as developed by my advisor Human Awadi. A kernel is quote unquote good. The premise is that the main premise behind kernel flows is that a kernel is quote unquote good if the number of interpolation points or the number of training points can be reduced without causing a significant difference in the interpolation, in the kernel interpolation. So to quantify this, we look at interpolation V with kernel K using the full data set versus W, which is the same interpolation but only trains with half of the set. And we construct this row to be the relative difference of these interpolations in kernel mode. So a kernel is good if this quantity is small. So the way this works in practice in the parametric kernel flows variant of the algorithm, we take the training set. We have a parameterized family of kernels. The user has to select which parameterized family of kernels they want to use. and an initial parameter theta. To evolve parameter theta from step n to n plus 1, one selects a batch of NF points, and out of this batch, they select a sub-batch. Then we interpolate with a batch, we interpolate with a sub-batch, we calculate rho. Note here that the V depends on parameter theta, and the norm depends on parameter theta. And we deform theta in the direction of greatest descent with loss function rho. So this is precisely a so this is just a gradient descent algorithm, and we can also do this with and we can also do this with an L2 loss function. In this case, the norm doesn't. In this case, the norm doesn't depend on parameter theta. Just FYI. And again, we can apply gradient descent on rho with loss function E2. The output of this algorithm is a learned kernel. We denote it as k theta star. And to see this in action, we again take an elliptic PDE. However, this time we assume that the coefficients A are in fact unknown, as well as U and F. We assume that what we do know is measurements of U on some finite set. And the question is, how can we accurately estimate both the coefficients and the signal U? We can approach this problem using kernel flows. We define our parametrized family of kernels like this, as Green's functions of this partial differential operator. Note that alpha, that the true coefficient isn't actually known. The true coefficient A isn't known by assumption of this problem. And we use kernel flows to optimize parameter alpha in the direction of greatest descent of rho. Right. So after an application of kernel flows, we can see that that our initial estimate of alpha is deformed in the direction of true coefficient A, and also that the recovery error is and that the recovery error of U is decreased by an order of magnitude over the life of the KF algorithm. The second variant of kernel flows is called the non-parametric variant. It assumes that we have the training set, and we select an initial kernel K. Now, what this variant learns, now the kernel that this variant learns is of this form, which is a composition of initial kernel K with some map F. In this case, F is initialized with the identity. To evolve from step n to n plus 1, F is simply, we simply deform F with gradient descent with respect to loss function rho. And again, the learned kernel is written as KF star. So to see this in motion, we look at the Swiss roll cheesecake example. We have one blue spiral with output -1, one red spiral with output +1. We have initial kernel. We take the initial kernel to be the Gaussian RBF kernel, and we see that the two spirals are nicely detangled, and all the red points end up on one side of the domain, and all the blue points end up on another side of the R2 domain. We can also do this for a larger spiral, for a larger Swiss roll cheesecake. The red points end up on this side, the blue points end up on this side, and the spirals are nicely detangled. We can also apply kernel flows to the MNIST database. MNIST, each MNIST image is a 28 by 28 image of a written digit. there are 10 classes, digits 0 through 9. Class 0 has output label. It's this one hot vector where the 1 is in the first component. Class 1 is one hot vector where the 1 is in the second component, and so on. We take a Gaussian initial kernel, and we can observe class-dependent archetypes in the flow. So what this means is in each 5 we see this tick at the upper right corner of each 5 and a bar at the top and this splotch to the side of each 6. So this flow has a nice property that it clusters images according to class. We find evidence of this by comparing the average pairwise distance, the average pairwise Euclidean distance between a pair of images of the same class and a pair of images of differing classes. We find that over the life of the KF algorithm, the ratio between average interclass image and the average in-class image is substantially increased. Also, we observe that when interpolating with this learned kernel from kernel flows, so if we train our data with only 10 points, meaning 1 point per interpolation, or sorry, 1 point per image class, so one image per. So it's 1 image of a 0, 1 image of a 2, or sorry, 1 image of a 0, 1 image of a 1, 1 image of a 2, and so on. If we do that, we have an average error rate that is actually comparable to interpolating with 6,000 6,000 random MNIST images. Moving on to applying kernel flows to artificial neural networks. ANNs, or artificial neural networks, are the go-to method for image classification, machine learning, artificial intelligence over the last decade. Mathematically, they have a very simple structure. It's just a composition of n functions. Colloquially, these are known as layers. Each layer is a composition of a linear part and a nonlinear function. But in typical or in most applications, people use the ReLU they use the ReLU nonlinearity. Excuse me. The parameters within each layer can the parameters of each layer are given by theta I, and the parameters of the entire network is in theta. In conventional examples, in conventional image learning examples, the most common approach is to use convolutions on small patches as this linear function. The first method of applying kernel flows to ANNs looks like this, where we define a parametric family of kernels that is the composition of the Gaussian RBF kernel with the output of a network with parameters theta. We can use kernel flows to learn the optimal parameter, and then we use Gaussian process classification to make a classifier with this learned kernel. We find lower error rates than conventionally trained CNNs. So in this example, a conventionally trained CNN would have an average error rate of approximately 0.7 to 0.8%. So it looks like we're doing about 0.2%, about 0.1 or 0.2% better than a conventionally trained CNN. Also, GPR, again, with only 10 images, is quite accurate. Excuse me. GPR with 10 images can also be very accurate compared to when using 6,000 images, especially in good selections of the 10 images. The second application to neural networks that we present with kernel flows, we construct a kernel defined with intermediate layers or hidden layers of the network. So here's our network. The definition of an intermediate layer is the output after the is the output of the first I layers. We can take all of the hidden, so we can take all the hidden layer outputs and put it into H theta, and we define our kernel as a composition of, and we define our kernel in terms of these intermediate layer outputs. And so now the process is we take the most commonly used loss function, cross entropy, and we can regularize it with our kernel flow loss function. And we can use this and we can use this KF regularized loss function to learn ideal parameter theta, and we use the network this time to construct our classifier instead of using. In this case, we don't use GPR to classify the images. We only use the output of the network. Note that this is more computationally efficient. GPR with a large number of interpolation points it scales as n cubed, so it's not ideal to use, for example, 60,000 interpolation points as an MNIST to construct a classifier. So this was inspired to reduce computational complexity from the first version that we examined in this talk. So this is a novel approach to applying intermediate layer outputs in the training alongside with the output of the entire network using KF regularization loss. To see this in example, here we have a relatively standard CNN for MNIST. We define a kernel based on the output of the sixth layer, the final convolutional layer. We have the entire loss function here, and we observe that this outperforms traditional training techniques using batch norm or batch norm and dropout, and also we can look at results on something called QMNIST. Now, what QMNIST is it's a resample testing set of written digits. So it's good to look at your error results, at your error rates on QMNIST, just to confirm that you aren't overfitting. You're not overfitting. You're not fitting the data. You're fitting the class essentially. So So KF regularization is good in that it is robust to this distributional shift in the testing set. We also find improved generalization gaps, meaning test error minus train error, and we find that kernel flows clusters classes in a class, or it clusters intermediate layer outputs in a class dependent manner. So when we use KF, the ratio between inter and intra-class images is increased compared to just using batch norm and dropout. The traditional methods of using batch norm and dropout. This can also be done for a wide ResNet. In this case, we construct a loss function with 4 KF regularizations on the end of the first, second, third, and fourth convolutional blocks. And we again observe improved results over traditional training methods, batch norm and dropout. we again have a robustness to a resampled testing set. So to summarize our kernel flow approach, a kernel is quote unquote good if it can model data accurately with a small subset. We learn kernels. So on a related note, we learn kernels which can classify accurately with only one example per class. And finally, applying kernel flow regularization to neural networks can train inner layer outputs as well as cluster them according to class. And we think this makes it easier for networks to be trained and improves testing error rates. Possible future work could include applying this KF regularization to other networks and other data sets such as speech recognition or video learning or video classification or some other class of data set. We also ask if we can make better layer combinations in the kernel. This wasn't explored too much in depth in this talk or in this work. And also, can we do better than the Gaussian kernel with is it possible to do better than the Gaussian kernel just with the fact in mind that that each of the outputs of each layer is actually an output of a convolution? Thank you so much for thank you so much for listening. Hope you have a great day.